Okay, I wanted to talk about symmetric matrices and orthonormal diagonalization. Okay, we are confining our discussion to just real matrices here. Okay, you can do some of this stuff with complex matrices, but we're not going to cover that. Before I do anything on symmetric matrices, I want to talk about something called the theorem on distinct eigenvalues here. I think this is worthy to know, even though it doesn't directly pertain to symmetric matrices. But let's go ahead and take a look and see what it says. If the characteristic polynomial of a real n by n matrix has n distinct real roots, okay, then there is a basis for Rn consisting of eigenvectors. That's what that says, eigenvectors of the matrix, okay? Alrighty. All right, so if you've got n distinct real roots, okay, or zeros if you want to call it, put it that way, then there is a basis for Rn consisting of eigenvectors of the matrix, okay? Let's go ahead and get an idea why this is true, okay? Here's why the theorem is true then. If the distinct eigenvalues, that means they're all different, right, are lambda 1 through lambda n, with corresponding eigenvectors x sub 1 through x sub n, respectively, okay, so this guy corresponds to this guy corresponds to that guy, and so forth on down the line, then it can be shown that these eigenvectors are in fact linearly independent, and since there are n of them here, they must actually span Rn, right? So they must be a basis, okay? Now let's get an idea of why these eigenvectors would be linearly independent, okay? So I'm not doing this in complete generality, but you should get the idea. I'm making it a little bit easier, I think, to get the idea across by taking just the case where, say, n is 3, and I think you'll be able to see how to generalize this, okay? So let's say x1, x2, or x3 are the eigenvectors corresponding to some 3 by 3 real matrix, okay, with distinct eigenvalues, okay? Okay, now remember eigenvectors, by the way, are non-zero here. Okay, now suppose I have a linear combination of those eigenvectors being the zero vector, right? I want to somehow show that these constants a1, a2, and a3 must be 0 also, okay? Now, here's what I'm going to do. Since these are just scalars, I'm going to take the first equation, right? All right, that's set to 0. Somehow trying to show the a's are 0. But let's say that's equal to 0. I'm going to multiply by the matrix A itself. So let's say A is my matrix, my 3 by 3 matrix with these eigenvectors, okay? I'm going to multiply by that matrix A on the left on both sides of the equation. And I'm going to do it again. I'm going to multiply by A one more time so that I've got these two equations here. Now, since these are just scalars, you see the A comes on the inside of the parentheses here. Okay, and so forth with the A squared. Okay, so you should see how the second and third equation just comes directly from the first. Now, the reason I'm doing this is because remember that these are eigenvectors, so A times x sub 1 bar should actually be what? A times lambda 1 x sub bar, because lambda 1 is supposedly the eigenvalue corresponding to that eigenvector. Okay, and I did that with all of these, so that the first line is a1 x bar plus a2 x bar, x sub 2 bar, plus a sub 3, x sub 3 bar is 0 bar, and then what? A sub 1 lambda 1 x1 bar plus a2 lambda 2 x sub 2 bar, and so forth. A sub 3 lambda 3 x sub 3 bar is 0. On this second one here, you're just going to use the fact that it's an eigenvector here. So as an exercise, show that a squared x sub 1 should be what? Lambda 1 squared x sub 1, and so on for these other ones, okay? So well, now we've got these three equations instead of these ones, okay? Now, I want to show that a sub 1 must be 0, okay? Now, to show a sub 2 and a sub 3 are 0, you'll do something similar. But I want to show a sub 1 is 0, okay? So I'm going to take this first equation and I'm going to dot product both sides with x sub 1. Okay, so you see I would get a sub 1, x sub 1 dotted with itself, x sub 1 dotted with x sub 2, x sub 1 dotted with x sub 3, and that should be x1 dotted with 0. And I do that with all three equations, okay? And notice that the dot product, that's actually a number, right? Okay, so there's no more vectors involved. And what these three equations become these three scalar equations, a sub 1, m sub 1, 1, plus a sub 2, m sub 1, 2, plus a sub 3, m sub 1, 3 is 0, and so on. You've got lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3 squared. Okay, what is that number here? M sub ij is the dot product of x sub I with x sub j. Okay, so that's what each of these means. So m sub 1, 2 would be what? X sub 1 dotted with x sub 2 and so forth. Okay, so those are just numbers, as you can see. Now I'm going to take this thing, and you see I can actually write it as this matrix equation. I've got this 3 by 3 matrix times what? This column vector a1 m sub 1 1, a sub 2 m sub 1 2, a sub 3 m sub 1 3 times this 3 by 3 matrix should be the 0 vector, right? Now, this square matrix on the left is what's called a Vandermonde matrix. Vandermonde, okay? It's actually a transpose of a Vandermonde matrix, but that's fine, okay? And this often appears in discussions of interpolating polynomials. If you look at that section in the book, this actually appeared, okay? It has a determinant that is the following, okay? P, this pi here, it's not, you remember sigma means sum? I don't know how familiar you are with this. Sigma means sum. Well, pi, this cap pi here, that's a cap pi, is product instead of summation, okay? So you're going to take the product. A Vandermonde determinant always has this property. You're going to have 1 is less than or equal to I, is less than j, is less than or equal to n. In this case, n is 3, right? That's a 3 by 3 matrix. But it's going to be lambda I minus lambda, or lambda j minus lambda I. It's the product of all those, okay? And in general, that's going to be like I have here. That's going to be n, okay? That's kind of cool. You can actually prove that using induction on Vandermonde determinants. Okay, there's other ways to prove it. But anyways, in this particular case where n is 3, that means lambda 3 minus lambda 2 if you were to take the determinant of this, okay? Lambda 3 minus lambda 1 times lambda 2 minus lambda 1. Because these are all distinct eigenvalues, notice that each of these factors is non-zero, therefore their product is non-zero. Okay? That's what I say here. What does that mean about this Vandermonde matrix up here? That means it's invertible, right? So if we imagine multiplying on both sides by its inverse, which exists, its multiplicative inverse, we could isolate this column here, that column right there, and we would discover that what? Well, it would be the inverse matrix times the 0 vector here, right? 0, 0, 0, and we would discover that a1 m sub 1 1 is 0, a sub 2 m1 2 is 0, a sub 3 m sub 1 3 is 0. In other words, this column vector right here is just the the 0 vector. Okay? All right, so we're almost there here. I would point out one quick thing here. Remember M11 is actually what? X1 dotted with X1, right? That was our notation. That is what? The square of the magnitude of X sub 1. That's not 0, right? Because remember, eigenvectors are non-zero. Okay, so M sub 1 is not 0, but I1 times M sub 1 1 is 0. What does that imply? I1 is 0, okay? Now, you could employ a similar technique here in a more general case, well, in this case, and find out that a sub 2 is 0 and a sub 3 is 0. In order to find a sub 2 is 0, what you would do is come back up here and you do the same type of thing, only on this, you would dot on the left on both sides of the equations for all three equations by x sub 2, okay? By x sub 2 here, okay? Then you would have actually in there that m sub 2, which is also non-zero. To get the rest of this would still hold, so that would prove that. And then if you dotted originally by x sub 3, you could actually work it down there and show that a sub 3 is 0. And the general case is very similar to what I've done here. Okay? Alrighty? Okay. Now, so far we haven't discussed symmetric matrices. Okay, the theorem on distinct eigenvalues that we just mentioned above asserts that there is an n by n matrix, or that an n by n matrix is similar to a diagonal matrix if its characteristic polynomial has n distinct real roots. Okay? But if the roots are real and some are repeated, then the matrix, I'm going to point out, may or may not be similar to a diagonal matrix. Okay? So in the case where they're not all distinct, different things can happen here. It may not be diagonalizable. Okay? Okay? So some further effort is required to see whether each eigenspace has dimension equal to the multiplicity of the root. Okay? Okay? So in the case of repeated eigenvalues, you may not have a diagonalizable matrix, but you still might. Okay? Might or might not. Okay, now here's where I want to bring in the symmetric matrices. I'm going to say this. But in the case in which the real matrix A is symmetric, that means equal to its own transpose, we can be assured that it is real diagonalizable. Okay? So it is diagonalizable, okay, or it has a real diagonal form, as we're going to see here. Okay, this is something called the spectral theorem in some people's parlance, okay? The spectral theorem, a real symmetric matrix has a real diagonal form, okay? Now, your book actually proves the following propositions here that build up to the spectral theorem, so I'm not going to prove these like I did the previous theorem, so you can go through those yourself. But let's talk about a couple quick propositions here. Proposition 1, eigenvectors belonging to distinct eigenvalues of a symmetric matrix must be orthogonal, okay? So eigenvectors belonging to distinct or different eigenvalues of a symmetric real matrix here must be orthogonal, okay? If A is a real symmetric matrix, then there is an orthonormal basis of eigenvectors of A spanning Rn, okay? Assumably A here is real n by n, okay? So if A is real symmetric, then there is an orthonormal basis of eigenvectors of A that actually span Rn, okay? Or an orthonormal basis of Rn, consisting of eigenvectors of A. Okay? Now, what does that mean? You remember from chapter 4? This means that A will have eigenvectors so that the matrix P formed from the eigenvectors will satisfy this condition. P transpose is P inverse, okay? P transpose is P inverse, okay? Remember we mentioned orthogonal matrices, okay? Or orthonormal. Okay, I guess they're called orthogonal, but they should be called orthonormal. Anyways, here, let's go through this. Thus, if A is real symmetric, then you can do the following. P transpose, which is P inverse, times AP is in fact D. Now in these cases, that's going to make it particularly easy to find the inverse, right? If you know that you're dealing with or an orthogonal matrix, to find its inverse, you don't have to go through a bunch of calculations on your calculator or calculations on paper or a computer or something. You can just find its transpose, and that's easy. You just interchange rows and columns, right? All right? So this is what we're saying, though. If A is real symmetric, then you can do this, and this is a real diagonal matrix, okay? So people usually call this orthogonally diagonalizable, okay? Kind of a mouthful, okay? Alrighty, let's take an example of this. Find an orthogonal matrix P such that P transpose AP is diagonal, okay, or D here. Now here's going to be my A. You can see it's 2, 1, 1, 1, 2, 1, 1, 1, 2 reading across. Okay, you can see that's obviously real symmetric. Okay, it should therefore be what? Orthogonally diagonalizable. Okay, so there should be a P that we can find here that, well, what? Will do this for us up here. Okay, now I'm taking this one here because you're going to see here. Well, let's go ahead and first of all, here I took to find the eigenvalues, right? I went the determinant of lambda I minus A. Okay, I didn't use X, I used lambda here. Okay, and you can see this is what you're going to get. Okay, to find the characteristic equation. This turns out, I did all the algebra on paper, but I decided to not write it here. But this turns out to be the following. Lambda minus 1 squared times lambda minus 4. Okay, so nice here, but you notice we're getting a repeated eigenvalue because I wanted to show you one of these here. So you couldn't, well, anyway. All right, so let's go ahead and see what you do here. Now you want to set that to 0 and solve. You can see the eigenvalues are what? 1, 1, and 4, right? 1 is repeated here. Okay, let's start out with that eigenvalue. Lambda is 1. Okay, remember lambda is 1 substituted up here. Okay, remember this thing is being set to 0. So that 1 minus 2 is negative 1 here. So we've got actually what? Negative 1 going down the main diagonal, and we've got negative 1 everywhere else here. So this is our matrix here. This is our augmented matrix. So we've got zeros over on the right. This actually gives a row reduction to this matrix. We basically just got 1, 1, 1 set to 0. Okay. Let me point out the dimension of the eigenspace will be what? The dimension of this matrix then. Okay. The column space will be 3 columns minus what? The rank is 1. So it'll be 2, which is exactly the same as the multiplicity of the eigenvalue here. Now, I went ahead and gave a name to the entries in the eigenvalue. I called it, or the eigenvector. I called them x1, x2, x3. So those are just the scalars of the eigenvector. Okay. Alrighty. Go ahead and solve this. So, you know, these other two equations, these are a waste of time now. 0 is 0. Yes, indeed. Okay, that's not going to help us out. Okay. There we've got this. Now, you can see the two free variables are going to be what? This is x2 and x3. So go ahead and solve for x1 in terms of x2 and 3. We would get what? X sub 1 is negative x sub 2 minus x sub 3. Okay? Now this is our, let's maybe call this our eigenvector. I'm not putting a subscript on that, by the way, because there's actually going to be 2 of them as a basis. Okay? But let's say this is our eigenvector, okay, one of our eigenvectors, x sub 1, x sub 2, x sub 3. X sub 1 is what? Negative x2 minus x3, x2, x3. Now you can see we can break this up, okay. Again, this is two-dimensional. We got x sub 2 times negative 1, 1, 0, plus x sub 3, negative 1, 0, 1. Okay, you can see that would be what? A two-dimensional subspace, okay. A two-dimensional column space there. Now, here's what you want to do here. Once you've found this, you found a basis for all your eigenvectors. Okay, again, x sub 2 and x sub 3 can't be 0 because the 0 vector is not technically an eigenvector. But don't worry about that anyways, okay? To make a space, you would just throw in the 0 vector even though it's not technically an eigenvector. Here's what you want to do. So I've got these two basis vectors. In this case, I've got negative 1, 1 and negative 1, 0, 1, right? Okay. Now what you want to do is go ahead and use the Gram-Schmidt process on those. Okay. And you will have 2 eigenvectors. Okay. There, you see that you can actually test that these are eigenvectors. And they're going to span exactly the same space. Okay. It's exactly the same space here. But they're going to be orthogonal, right? They're going to be orthogonal. You can double check quickly that these are in fact orthogonal, you can see their dot product is 0. Okay, and I promise this second one is a linear combination of the first two. Okay. Anyways, let's get to it here. Okay, you want to go ahead and normalize these also. Once you found these are what your these have been you've gone through the Gram-Schmidt process and your eigenvectors. You want to go ahead and normalize those. Okay, so now they're orthonormal. Orthonormal means what? They're orthogonal. Okay, pairwise orthogonal, and what they have magnitude 1. Okay, all right. So these are going to be the first two columns of my p vector. Okay, all right. Remember, we're trying to find p for this up here. Now, technically this, right? Okay, that'll get us that. Okay, so we've got the first two columns. Don't forget we have one last, what, eigenvalue, which is 4. So coming back up here on this, okay, we're going to get lambda equal 4. And you can see we would have, what, 2's down the main diagonal. So here's our matrix. Okay, augmented matrix. It's set to 0. And then row reduced echelon form goes down to this. Okay. And an eigenvector would be 1, 1, 1, right? The non-zero span of 1, 1, 1 would be the set of all eigenvectors corresponding to that eigenvalue. Okay, and then I'm going to go ahead. Did I write that down there? I didn't even label those. But I'm going to put a hat on top, right? That's my notation for a unit vector. I'm going to divide this by its own magnitude. I get 1 over the square root of 3 all the way down. And then I'm going to pack those three matrices, or those three vectors, sorry, into a 3 by 3 matrix, and that's going to serve as my P. Okay, you can actually show this yourself. You could do it on your calculator. That's what I did, just to double check and make sure I didn't screw up. But I went P inverse minus P transpose on my calculator, and I got the 0 matrix, okay? And what you would ultimately have then is, I guess I should call this D. Okay. P transpose a P, right? It should just be a diagonal matrix consisting of the eigenvalues. In this case, in the order we would have them 1, 1, and then 4, okay? And then likewise, we could write A equals P D P inverse, but that's P transpose, right? Okay. And then we could start doing things with A, like we did before, taking high powers or doing other things with it. Okay? Okay, well, I hope you understood that and you're able to work those problems in that section. Okay.